Well, thank you all for joining us today in this Origin seminar. It's a pleasure for me to introduce Javier. I have known him for a few years now, and he's kind of my older academic brother. So I think we both did our PhD with the same supervisor, but with a slight difference of New Year's. So he received his PhD from UNAM in Mexico in 1999 after a pre-doctoral fellowship at Harvard University. Then he later held a postdoctoral position at the American Museum of Natural History and a sabbatical appointment at the University of Heidelberg. He's the author and co-author of a long list of publications, and his contributions have been recognized with the 2009 Prize for Scientific Dissemination in the state of Michoacan in Mexico. And in 2017, the Bessel Research Award from the Alexander von Humboldt Foundation in Germany. Currently, he serves as Vice President of the Astronomy Division of the Mexican Physical Society, and is member of the Scientific Editorial Committee of the Revista Mexicana de Astronomía y Astrofísica, Mexico. He is a researcher now at the Institute of Radio Astronomy and Astrophysics in Mexico, where his work focuses on the formation, evolution, and dynamics of interstellar molecular clouds, the process of star formation, and the early development of stellar clusters, all of this primarily through large-scale numerical simulation on supercomputers. So please, Javier, you can go ahead.
Thank you. Thank you, Griselda, and thank you for everybody to invite me to talk about my work. So as you can see, the title of this talk is Gravity or Turbulence, the Energy Budget of Molecular Clouds and the Star Formation Law. But probably a more commercial title will be The Turbulent Life of Collapsing Clouds. It's a little bit less boring. So for those that with ISM, let me tell you that 1917 by Wilson and Penzias, the same guys that discovered the background radiation, and also Jeffers. Yes?
We will ask you for...
Could you start from the beginning?
Yes, I just got a message saying that my connection is unstable. So I hope it gets better. I'm not on Wi-Fi, I'm on a wired network, so it's the university connection, so I hope it works properly. Okay, so let me repeat then. So the first detection of CO was made in 1970. And it was made by Wilson and Penzias, the same guys that discovered the background radiation, the cosmic background radiation, with the help of also Jeffers. So that was like 50 years ago, almost 60 years ago. This was the first detection. And they one of the things that they point out is that the width of the line is supersonic. So people try to understand why the CO line towards the Orion Nebula was supersonic. And one of the first, if not the first model of molecular clouds was made by Goldreich and Kwan. And they say that they argue that the clouds should be in state of collapse or can be in a state of collapse, and that may explain the line width. So, but the first year, a few months later, Zuckerman and Evans dismissed this idea because, as they argue, large global collapse of clouds will imply a very large star formation rate. So, in a sense, they argue that they must be supported by turbulence. At least they suggested that clouds should not be dominated by large-scale systematic motions, but by local motions. And by local motions, people understood local turbulence. I'm not going to argue that clouds are not turbulent. Of course they are, because they have huge Reynolds numbers. So basically, any motion in a molecular cloud will be turbulent. So that's not the point. The point is whether turbulence can provide support to clouds such that they can be long-lived. They can such that they can live for many different free-fall times, in a sense that that they can reduce the star formation efficiency. So let me start with this idea. The Beer parameter is, by definition, is this ratio of 2 times the kinetic energy of the gravitational energy. And if you plot, for instance, the Beer parameter against the mass of clouds, well, you will argue that if the Beer parameter is equal, the cloud is in equilibrium. If it's smaller than 1, then gravity dominates, then it should collapse. And if it's above 1, then the cloud will be supported against gravity because of these turbulent motions. So the first point to notice is that if you follow the collapse, then at some point you will develop larger velocities than 1, larger BL ratios than 1. Because actually the free fall time is the free fall velocity, is larger than the equilibrium velocity. So you can have clouds that have, in principle, real parameters above 1 and still be collapsing. The real parameter, since it has the velocity dispersion squared, doesn't know the direction of the motions. So that's something to keep in mind. But probably more important, if you have, for instance, a simple cluster of stars and you let it go just by the gravity and see what happened after 1 free fall time. So all this process is collapse. So you start here. I'm plotting the virial ratio against time for a simulation. We started the simulations with a virial ratio smaller than 1, substantially smaller, and we focus on what happens after 1 free fall time. And as you can see, after 1 free fall time, you reach virial equilibrium. So virial equilibrium, in a sense, is the very result of collapse. So in the case of clouds, you can be compressing a cloud, you can be forming a cloud by the compression of H1 streams. The H1 is thermically be stable, so it can be warm and diffuse or dense and cold. So as soon as it shocks, it creates denser regions that get cooler, and then they don't have enough thermal support to avoid collapse, so they start collapsing. So what we measure in this kind of simulation is precisely that at the beginning, in the early stages of the simulations, you can have a larger kinetic energy compared to the gravitational energy. But as you build up your cloud, your dense gas, then gravity takes over, and then it takes with it the kinetic energy. So the kinetic energy follows the gravitational energy because the cloud is collapsing. So and actually the ratio is more or less virial. So since this simulation is built by constructing the cloud from the larger scales, the time span is larger than 1 free fall time because we are adding more mass in this simulation. So what I will argue is that just pure collapse produce a virial relationship, and this has been tested through simulations of gas collapse and also through just embodied simulations. So here is this plot by Larson in 81, that very famous plot between the virial ratio and the length of the clouds. And what Larson showed is that the most of clouds, so basically all the clouds that he saw, were in a virial ratio of 1. So the idea was that clouds should be long-lived and supported by this turbulence, supported against gravity by this turbulence. But and in a sense, more recently, when people focuses and look through clouds, you can see that there are many clouds that have over-virial parameters compared to low virial parameters. So here is plot the mass of Milky Way clouds against the virial parameter. This is for CO from the survey by Tom Dane. The analysis was made by Miguel Deschamps. And you can see that there is plenty of clouds that look over VIA or that are over VIA. The same analysis was made by Evans. He took a couple of different surveys, the Deschamps and also the Rice survey, and he found a large population of clouds that appear to be unbound. Okay, so observations suggest apparently that 2/3 of clouds are unbound. Here is a similar plot. In this case, I'm plotting here sigma square over r. So if you believe in Larson relation, this should be constant because the velocity dispersion scales as the size to the 1/2. So this should be constant as a function of column density. So in principle, the velocity dispersion size relation should be just a line here in principle, although the second Larson relation says that the column density is constant. So Larson relation is just a point here in this plot. However, if you look at different clouds, the external Milky Way, the different regions in different galaxies, you see a distribution here of data points. By the way, alpha equals 1 is this line over here, and alpha equals 2 is a little bit above here. So the virial parameter, in a sense, is proportional to is perpendicular to this line. So just to show you this, the kinetic energy is proportional to sigma square. The gravitational energy is proportional to m over r. So if you divide by an extra r, then you have the two axes of this plot. So basically, we are plotting in a different way the virial parameter. Okay, so this is a question that different people has asked us in different ways. Basically, is if all cores were gravitationally bound, the star formation rate and the efficiency will be significantly higher than observed. Yet most of the cores we analyze, as well as those of Herschel catalog, are unbound. So this is from a recent email by Fumitaka Nakamura to me, but the same question has been asked in different places. So let me start with this part.
Javier?
Yes.
Are we allowed to interrupt with questions? I'm sorry.
Yes, of course. Sure.
I have a question at this point because I think it's important for core dynamics to understand what you mean by, but what is meant by unbound there. Does that also include external pressure as a potential bounding energy in that, or is it just the virial kinetic energy and gravitational potential energy?
Basically, yes. Basically, what people call an unbound core doesn't takes into account the pressure, the external pressure. It's just the internal pressure. Basically, what people argue is that for these clouds to survive many freefall times, you need to be bound by different pressures. So here is the virial pressure term, that surface pressure that has to be confining these clouds, for instance, 10 to the 8 in terms of P over K, no? So 10 to the 7. So these are the different pressures that you require for these clouds to be bound, okay? But yes, in principle, when people talks about unbound or bound, it's just the virial parameter. In some cases, especially in numerical simulations, people also talks about the magnetic energy, but that's difficult to quantify in observations. So yes, let me focus first in this part about the overvirial cores or overvirial clouds. In principle, it looks like why we insist that clouds must be in a state of collapse, no? If the evidence shows that the virial parameters are large. Well, this is something that goes back to when I was doing my PhD 25 or more years ago. Basically, I was trying to find how turbulence could support clouds. And since turbulence has most of the energy on the larger scales, and that energy is transferred to the smaller scales, I was trying to find that whether clouds could be supported or not. Unfortunately, all my simulations didn't show that you could actually support clouds by turbulence, because turbulence dissipates very rapidly. So unless you keep your source of turbulence constantly driven in an homogeneous way, you will have collapses. So one of the ideas was to build up a cloud in first place by the compression of larger scale streams. Here are two different works, numerical works, one by Haich and collaborators, the other one by Vázquez et al. And what we found is that you always end up collapsing. So the turbulence that could be transferred from the larger scales to the smaller scales doesn't help you to avoid collapse. So the previous simulations was made without feedback. In this case, this simulation has feedback, and well, you still see collapses. Of course, you form the stars there. You can see the dark points, and then the feedback disperses the cloud. But it's not that this region is not collapsing. This region is collapsing, and all the dense molecular gas is locally collapsing. Is not collapsing into a single center. You have different centers of collapse. And what actually prevents the cloud to fully undergo collapse is the action of the stars. So it's an external source of energy, not properly the internal turbulence of the cloud. So this is basically our point, no? So so yes, there can be a lot of cores over here. Still that appear over virial, but one of the things that has to be taken into account is that when you allow a cloud to collapse, then you form some structures, and those structures don't have a well-defined identity. So you may find here different cores that you may think that they will end up collapsing, and they actually collapse into something else, into a larger structure maybe. So one of the possibilities for these clouds to exist still in a collapsing situation is that they are not cores that are going to collapse by themselves, but that belong to a larger collapsing situation. And this is something that is been that we are analyzing right now. And indeed, we found that different cores here have this effect. So in a sense, the tidal streams of this, the tidal force of these cores disrupt the core, imprint enough kinetic energy to these cores to disperse, to become not unbound. So, but anyway, that doesn't mean that they don't belong to a collapsing situation. So, and that is something that may occur in other clouds. So we don't know. That's something that we have to investigate a little bit more. Another interesting thing is that when you compute the virial parameter, typically you compute the gravitational energy, the kinetic energy of the gravitational energy. And well, you may find that indeed there are a lot of cores that appear over virial. However, one thing that you have to take into account is also the tidal forces. So if you consider the tidal forces, the interesting thing is that the gravitational energy that gives you these tides, these external tides, are also relevant and help you to disrupt your cloud. So this analysis was made on simulations of galaxies, and from those galaxies we took the clouds in there, and we try to analyze the virial parameter, but consider not only the self-gravity of the cloud, but also the gravity of the external field. Basically, the interesting thing is that it's not exactly the gravitational field of the whole galaxy, but the gravitational field of the nearby clouds. So you have most of the clouds in the spiral arms, and the neighbor clouds may exert enough tides to give you some tidal energy, kinetic energy that will help you to not collapse. Okay, so here, then what I am showing you is this simulation, this animation of this cloud that is undergoing collapse. And as you can see, there are different cores that appear and disappear as the collapse goes on, and that may explain then the large scatter in the virial parameter. So we have these two effects. So yes, there may be a bunch of cores and clumps that you can find with your clump finding algorithm that may belong to a collapsing cloud, but still those will exceed supervirial values. So let me now go for the first sentence in the previous note. That is, if all cores were gravitationally bound, then shouldn't the star formation rate and the star formation efficiency be sufficiently large compared to observations? Well, yes. In a sense, well, that's what we will think in first place. But let me show you here an analysis that we made using simulations of collapsing molecular clouds. This is published in a recent paper. We tried to compare to follow the same analysis that Pockrell made for molecular clouds in the solar neighborhood. So in this case, here is the Kennicutt-Schmidt relation. So this is the column density of star formation rate against the column density of gas. And all these clouds exhibit a very nice power law. This power law has a slope of 2. By the way, if they divide the column density of gas over the free fall time, then the slope switches from 2 to 1 in this case. But this is the same set of simulations, just in this case dividing by the free fall time. So basically, they showed that these are the typical star formation rates that they found in local clouds. All these clouds are in the solar neighborhood, and the star formation rate was made by counting class 0 objects. So embedded objects, they estimate the lifetime and the mass of the objects, and they count the objects to estimate the column density of star formation rate. And this is just made by through observations of Herschel, the column density of gas. So we repeat the analysis that they made. Here you have the first plot, the column density of star formation rate against column density of molecular gas, and here we divide by the free fall time. And the green area is the area that Pockrell found in both cases, and the lines are our result. So basically, collapsing clouds in our case, following the same procedure that as they did in the observations, we try to reproduce it in the simulations, and we found basically the same star formation rates. In terms of the efficiency per free fall time, this is a parameter that defined by Krumholtz. They found that this parameter goes between -1 and -2 in log scale as a function of the column density of the gas for the different clouds. And we found more or less similar results. We actually have two different types of simulations, one more filamentary and one more like a hub thing, where you have a hub and material falling into this hub. So basically, collapsing clouds can produce similar Kennicutt-Schmidt relations, and they can produce also low efficiencies per free fall time. So you may wonder, well, why is this so? If they are collapsing, why shouldn't the star formation rate be very large? Well, in a sense, yes. Let me plot here the mass in Wisos. Let me just take out here because I have a zoom bar that is that blocks me the plot. So I have time here against the mass in young stellar objects for a simulation, and if you have collapse, then what you will have is that indeed the mass increases, the mass in young stellar objects increases, and also not at a constant rate, but the rate is increasing actually. So the instantaneous star formation rate can be large, and it's large in our simulations. However, if you follow the observational procedure, it turns out that you are dividing over a much longer time scale. So in this case, your the star formation rate that you will be deducing is much smaller. And we believe this is something that happens in the observations because they are taking averages, they are assuming long star formation time scales. So that's something that has to be taken into account. Yes.
Javier, in that last plot, where would the free fall time be on that time axis?
I didn't. This is just a schematic. I didn't put it.
Oh,
But in
okay.
principle, let's say that it's around here. So of course, this goes. Typically, it depends, of course, on the initial conditions, but I can tell you that we have simulations that after one free fall time have efficiencies of between 16% to 60%, no? So it depends a lot on the boundary conditions, on the initial conditions, on the initial energy input that you have in your motions, in your turbulent motions. So it's not a unique value. Certainly, I'm cutting here before one free fall time, and that's what we did in the simulations, no? So yeah, but what we feel is that you can, if you consider longer time scales than what actually should be considered, the instantaneous rate can be very large right now. For instance, in Orion, but still people is taking an average star formation time scale of say 500,000 years, and that lowers a lot the efficiency per free fall time or the instantaneous star formation rate. So, okay, so these are the simulations that I was talking about, and what actually prevents a large star formation rate, as I already mentioned, is the feedback from the simulation, from the stars, but not the internal turbulence. The local collapse still occur unless the heat and the H2 region disrupts the cloud. But if you let it go, it's the internal turbulence cannot prevent collapse. This is basically the point. So what are we measuring when we measure the velocity dispersion of clouds? Are we measuring the energy input of these stars, or are we measuring the velocity dispersion of the dense gas that has not been affected? Because if it were affected, then it will not be any more molecular. It will be atomic or even ionized. And this is something that other people also have seen. So we are not the unique people that has been simulating clouds that are collapsing. And of course, you need the star formation, the feedback to prevent and to avoid collapse and to disrupt collapse. So it's not the internal turbulence, but the external, in a sense, feedback from the stars. This simulation is very nice. They have a very nice animation by Kim and Stryker. It's worth looking at the animation in the APJ. So, and this is something that I actually found when I was doing my PhD thesis. I found that indeed, when you look into the clouds, you can see that the clouds were rapidly dispersed by the stars. This cloud that you see here was formerly here, and those stars start dispersing the cloud and push it over here as more star formation came into these places. So the size of the cross was reflecting the age of the stars. So yes, basically this is something that we found many years ago. I never published this result because those were 2D simulations, and I thought that they were that probably my feedback energy was not properly taken into account. It was just an approximation, a very rough approximation. So I never published this result. But we were looking basically this result, that you need the feedback to prevent collapse and to disperse the cloud. So is it possible for the star formation rate to remain low in gravitational collapsing clouds? Yes. So they may have a high instantaneous star formation rate, and star formation is what shuts down the star formation. And in these collapsing simulations, the star formation rate and the star formation efficiency are not large. So for almost 2 decades, there have been some debate between a couple of groups supporting collapse and most of the people supporting turbulence. Well, I think that there are different observational tests that have been done, and in a sense, both groups have been showing that the simulations of turbulence or simulations of collapse can somehow reproduce. So let me give you a brief summary. For instance, overview parameters of molecular clouds can be due to turbulence. There are different works. I'm just quoting a couple of works here. In terms of collapse, well, you have during the process of construction of the cloud, you may have these overreal clouds. And also, as I show you, as I comment regarding the tides, clumps are part of cloud complexes, and then the other clouds can exert some external tides that will prevent collapse. And that's why you will see them overreal. In terms of the core-to-core velocity dispersion, well, I don't know about any turbulence work, but certainly we did an analysis of this core-to-core velocity dispersion in collapsing clouds, and we found it consistent with observations. In terms of the star formation histories, well, Krumpholz will argue that they are consistent with turbulence. We have made analysis of different regions of star formation, showing that star formation histories are consistent with collapse. In terms of the Hegel relations, for instance, PAD1, but also many others have shown that turbulence can reproduce the Hegel relation. We also did this in 2011. The same for the PDF. The PDFs, both groups have been showing similar, have been able to reproduce the PDFs of clouds. In terms of the IMF, well, there are different analytical, semi-analytical models that, based on turbulence and somehow collapse, trying to explain the shape of the IMF. In terms of collapse, at least for the salpeter slope, we have argued that collapse can reproduce easily the salpeter slope. In terms of kinematics of the newborn stars, I will talk a little bit about this in a few moments. But there have been some arguments about turbulence, but also we have made some analysis in numerical simulations, but also comparison with observations. So there are, I should say that still the debate is on the air, that the different groups have been able to compare, to argue against one or the other model. But let me just go through these points. So can non-collapsing molecular clouds exist in the solar neighborhood? What about the differential via parameters, the turbulent and thermal Gibbs masses? And what about the kinematics of newborn stars? So in terms of collapsing clouds, can non-collapsing molecular clouds exist in the solar neighborhood? Well, in a recent paper by Jose Franco, where I am also a collaborator, we made a semi-analytical model for the star formation rate based on the UV radiation, whether the radiation can be shielded, whether you can form molecules or not. And we found that if your cloud is somehow in vertical equilibrium, you can reproduce the observational points. So our model is shown in the lines, with the lines, and the colors are the regions where the observational data are more or less. So in terms of the column density as a function of size, we found that this is the radius of the galaxy, and we saw that you require, for instance, in the solar neighborhood, to have at least 30 solar masses per square parsec of column density to become either self-gravitating and molecular. If the column density is smaller, you can be molecular, but it not necessarily is self-gravitating. So you require some column density to actually have enough gravity and collapse. So And if you compare this to the data distributions of clouds in the Milky Way as analyzed by Miguel Deschamps, you will see, well, okay, all these clouds above 30 will collapse and all these clouds will not collapse. Okay, yes, that's from this analysis. But if you see the actual PDF, column density PDFs of local molecular clouds in the solar neighborhood, basically most of the gas, which is molecular, is basically already in this regime. So what I'm saying is that indeed in the solar neighborhood, you can have clouds over here. You could have, but they are not. Local clouds are not in this regime, are already in this regime. So what I think it's somehow happening is that, well, if you consider the galactic disk, you have, statistically speaking, you may have that the gravitational force, the vertical gravitational force, should be balanced by the pressure gradient of the ISM. So basically, what you have is that you can infer what is the typical pressure in the ISM given by the weight of your gas above, and the gas is waiting because you have either the gas itself, but also you have stars, and to some extent, also the dark matter can have some influence in the vertical direction if you are far from the center. So what we say is that the ISM pressure is more or less 6 times, it can be 6, 8, more or less, times the thermal pressure. And by this, we are parameterizing in this ISM pressure, the magnetic field pressure, the cosmic ray pressure, all the pressures are in there. But the point is that your star formation disrupts the thing, imprint a much larger pressure compared to the typical pressure ISM, such that what you create is bubbles that expand, that pushes the gas and compress the gas and form clouds in other places. So basically, you have clouds. Indeed, you have clouds that are being compressed by these star formation events. So in this sense, yes, you have a typical ISM pressure, but your clouds are much larger, have larger pressures because they are being compressed, and this compression will cause them to collapse. So in principle, what we found in Franco is that the typical column densities for formation of H2 are mean value estimations in this model, but actually at least local molecular clouds have in practice larger densities. So regarding the visual parameter, let me show you, here is a work by Peretto. Here is this plot, the Heger plot that I was showing you, which is more or less also the visual parameter ratio. You have here the velocity dispersion over the size to the 1/2 against the column density. And what Peretto argues is that all these clouds, in principle, these clouds over here are collapsing, while these may be more stable. Okay. In that sense, Kromholm, Lada, and Forbig, in a recent paper, analyzed a simulation where they have a cloud that is collapsing, that is undergoing collapse. And what they argue is that either the visual parameter or this Heger relation have visual parameters that increases with time at the beginning, and only once gravity has taken over, then the visual parameter profile is flat as a function of the column density. The same is for this plot, of course. You have visual parameter constant along these lines. So at the beginning, it increases, and then later on, it becomes flat. But basically, it's the same plot, these two. So they went then to actual observations in Andromeda. I believe it was Andromeda, one of the local galaxies. And what they argue is that 2/3 of the clouds in Andromeda exhibit visual parameters that increase with column density, and 1/3 of the clouds that have flat or decreasing visual parameters. So they argue that these clouds should be in equilibrium, while these clouds should be collapsing. Well, this is basically the same thing, what I'm saying you. And I did experiment very rapidly with my old simulation back in 2015 of a collapsing cloud, just to see what happened to the virial parameter. Here I have the virial parameter as a function of column density at different time steps. The first time step is the black one, and at the beginning it goes up, and then so the blue are a little bit later times. Then it goes to the green, yellow, and to the red. This is one free fall time, all these different lines. So yes, at the beginning, after one free fall time, you have nearly flat virial parameters, but most of the time you will argue that this cloud that is clearly collapsing will be under the eye of Cromholt. You will argue that this cloud is supported and is in equilibrium, which I think is wrong. So yeah, so although these guys argue that the collapsing clouds should exhibit flat or decreasing virial parameters, what we found is that most of the process of collapse exhibit virial parameters, increasing virial parameters, and it's just at the very end when you have this flat with these flat profiles. About the turbulent versus the Jeans mass, well, the Jeans thermal mass goes as c squared, the velocity, the sound speed to the square, times the density to the minus 1/2. And you can propose a turbulent Jeans mass similar to this one, but you just switch the velocity, the sound speed by the velocity dispersion. So in that case, you can prove that, well, the number of stars should be proportional to the Jeans number. So the mass of the cloud of the Jeans mass. So in both cases, no? We think that this plot by LADA, where they count the number of protostars and they found that those are proportional to the cloud mass, in a sense should be showing that clouds are actually collapsing and are forming stars from collapse. We have extended this relation to other cores over here. The Palau cores are much smaller. The LADA clouds here are these yellow data points. So with other surveys, we also fit another order of magnitude in cloud mass. So we believe that most of the clouds must be undergoing separation. How do you say? Fragmentation. So to our eyes, the turbulent Jeans mass does not appear to govern the star formation efficiency because all those clouds have different velocity dispersion. So all those clouds don't have the same Mach number. So you cannot apply the same recipe for the turbulent Jeans mass. So in terms of stellar kinematics, I'm about to finish. So let me tell you the following. If you have a cloud that is collapsing, the gravitational potential is varying in time, it's changing in time, and it's changing strongly, and that's what is driving the motions of the stars. So as Littenbell showed many years ago, if you have a process of collapse, that's a process of violent relaxation, and as a result, the velocity dispersion of your stars does not depend on their mass. So you should have flat velocity dispersion when you plot the velocity dispersion against mass. So basically this plot, velocity dispersion against mass, and it should be flat if the clouds that gave origin to that cloud, to that cluster, collapse. So we made the simulations, different configurations, colliding streams, just boxes that were going under collapse, something with some rotation, and so on. And we found every time we follow the collapse, we found this flat velocity dispersion as a function of time. These look like histograms, but those are not histograms. What the idea of having these boxes is because since you need the velocity dispersion, you need many stars. So we divide in beams the mass range in beams of the same number of stars, such that every beam has a similar statistical significance. So that's why they look like histogram. But those are actually plots of velocity dispersion against mass, per mass being said. What about turbulent simulations? Well, in the case of turbulent clouds, we have a velocity dispersion that increases with mass. Actually, we were expecting the opposite case, that if there were energy equipartition, the smaller stars, the stars with less mass, should have larger velocity dispersion, but clearly this is not the case. So we were wondering why this is so. So we analyzed our simulations in this paper by Camacho and collaborators, and we found that indeed low mass, they more or less start with similar velocity dispersion. These are these three different simulations, but as time goes on, you see that the velocity dispersion of the high mass stars is larger than the velocity dispersion of the low mass stars. So why this is so? Well, this is a plot of velocity, the velocity of the stars, yes, as a function of mass. The circle is the moment in which the star is born, also for the triangles and the stars. These are different range of masses. And you see that basically the low mass stars have very constant velocity, but larger as they become more massive, or as the massive stars are born, they have a much larger velocity fluctuations with time. So why is this so? Well, if you look at the simulation themselves, what you can see is that the massive stars, which are the green here, are located in denser places, statistically speaking, compared to the low mass stars. So this is a plot that shows that. This is the time, this is the density, and you can see that the green lines are, statistically speaking, above the purple ones. So they live in, statistically speaking, in denser places in these turbulent simulations. And here you can see that indeed they live in denser places. The x-axis is density, but also that allows them to accrete more masses. This is the typical accretion rate along their life. And you see that they, of course, accrete mass, and that's one of the reasons why they become more massive. So what it tends to happen is that in the simulations, the gravitational potential is not changing strongly. So that allows to the stars to become entangled, locally entangled between them. And then since the more massive stars are in a little bit lesser places compared to the low mass stars, they become more entangled. And as they accrete more mass, then this entanglement becomes stronger, and the velocity dispersion increases. So this is what we found. We call this dynamical heating of newborn stars driven by accretion-induced orbital tightening. So basically, it's yes, they are falling into local gravitational potentials, but what is driving their motions, the velocity dispersion, is not the global collapse, but the n-body dynamics. So this is what we found. This is what explains this velocity dispersion against mass as a function of time, increasing for more importantly for massive stars. And so, okay, we have these two cases. Collapsing clouds should exhibit flat velocity dispersion. Turbulent clouds should exhibit dynamical heating of massive stars. What happened in actual clusters? Well, we went to analyze the Gaia DR3 data, either of the Orion Nebula cluster and the Lagoon Nebula cluster. Those are more or less close. And we found quite flat velocity dispersions. So this is, in a sense, another way to prove that at least these two clusters have been formed by the collapse of their parent cloud. So let me then just put my conclusions here, and I will be happy to hear your questions.
Do we have any questions in the room? For people online, if you have any questions, please raise your hand and or you can just type them into the text chat. Questions?
I have a question. Hi, Javier.
Hi.
In your plot of the star formation rate versus column density or column density over the freefall time,
Mm-hmm.
for the clouds, the Milky Way clouds, Orion is kind of low. So
Say that again. Sorry.
in that plot, Orion is like below the other ones, right?
Yes.
Particularly
Yes.
low. Is that because star formation there have been happening like just for a short period of time, or is because
No, no.
gaining
No, I believe that's because of an area. That's very tricky because what you will think in first place is, well, Orion is the most vigorous region in the solar neighborhood forming stars, no? Maybe Monoceros also has an important star formation rate, but here you see that Orion is just in the very low end. And that's because you are dividing by the area. Orion is a huge cloud. If you take into account the whole area, then of course it will be the star formation rate will be very low. But if you focus only on the Orion Nebula cluster, then the star formation rate is very large. Yeah, but it's tricky indeed.
And a second question, now in different conferences, I've been hearing about the magnetically regulated star formation
Mm-hmm.
and comparing to the turbulent and gravity scenario where that is located. It's in between, or to your opinion?
Well, this is a point that has been addressed or has been repeatedly appearing in conferences in the literature. The point is that if the magnetic field is strong in first place, it is too strong, then you cannot collapse. The simulation cannot collapse. The cloud cannot collapse. It has to be already has to have a small relevance. But the funny thing is that if it has more relevance, as your cloud collapses, it increases the density of magnetic field lines, sort of speaking, and then increases the magnetic energy. So at the end, collapse also produces equipartition with magnetic field. So the fact that these three energies are similar, to me, says that indeed gravity is taking over. Gravity is collapsing, and that's what is driving the increase of kinetic and magnetic energy. So that will be my take. Of course, magnetic fields can delay collapse. Of course, it will be harder. Of course, also cosmic rays, because they will interact with the magnetic field and then will start producing motions of the magnetic field lines, and of course induce motions of in the cloud. But we don't know much about the diffusion coefficient of the cosmic rays. But yes, all these effects can lower the efficiency. However, if you take a very subcritical cloud, so a very strong magnetic field, the cloud never collapses. You have to have a lot of time driving mass through the field lines to concentrate the mass in some place, and then that may allow to become supercritical and then collapse. So it's I think it's a little bit tricky. Yes, they matter, but either they matter too much or they just delay a little bit the collapse. But it's not that they are going to be, in my impression is that they are not going to be the relevant quantity to explain the star formation rate. I think that the star formation process stops because of star formation feedback, and that limits the star formation efficiency.
Thank you.
Have any other questions? Not, we thank our speaker again.
Thank you.